Hello class. Today we are going to start with Case Study 2B Notes Part 1, Intro to Case Study 2B. Okay, so we're going to start with the case question. All right. Is there any reason to believe that the GPAs of students taking statistics are different from the university as a whole? Could there be some factor or set of factors that draws students with grade point averages lower or higher on average than the general population into introductory statistics classes? Not everyone takes statistics in college, but among those that do, are their GPAs different than the average GPA of all students? Implicitly, it is commonly believed on most campuses that some courses are easier than others. This almost has to be true by definition. However, are the GPAs of students required to take introductory statistics classes really any different than the average overall? Okay, so that's kind of the introduction. And now let's read our actual case question 2B. A statistics instructor used an online databank to record the GPAs of the 90 students that had enrolled in his introductory statistics class over the last 2 years, from 2014 to 2015. The GPAs were collected at the time the student began the course, and the average of the 90 GPAs was 2.733 with a standard deviation of 0.762. The most recent report for 2012 in University Literature states that the average GPA of all students having completed at least one semester in residence at the university is 2.889. Is the GPA of students enrolling in introductory statistics significantly different than the university as a whole? Okay, so that's our case question. And just go ahead and notice that I did go ahead and put the histogram here. So what shape would we, anytime we see a histogram, a good thing to start with is, okay, well, what shape are we dealing with? All right, so you can go and you can draw over it, and you see that that's a skewed left. Okay, anytime we have the tail going down and out to the left means that it's going to be left skewed. All right, so my first question is that, do you notice any differences between case study 2A and case study 2B? Okay, and the two main differences that I see here, first one being the sample size here is much larger than case question 2A, okay? Here, we're talking about 90 students. 90 students that this instructor collected GPAs on, okay? So N is 90. Our last problem, N was, I think, 18, all right? So here in case question 2B, we're gonna see what we're gonna deal with when we have a large sample, okay? Another difference that we have here from case question 2A is that this is a two-tailed test. Okay, what word in here lets us know that this is a two-tailed test? Different from. Okay, so here is the question. This is what we're going to use to form our alternative hypothesis. Okay, is the GPA of students enrolling in introductory statistics statistically significantly different than the university as a whole? Okay, different from. All right, so this is a two-tailed test. Okay, one similarity that case question 2A and 2B have are, we are both talking about averages in case question 2A and 2B. Case study 2 as a whole is our one population average case study. Okay, so from case study 2A, the test statistic that we learned was T. And T has a few requirements, okay? So the first question is, can we use T as the test statistic? And in order to answer that question, we just have to know, well, do we meet the requirements for T? Okay, the requirements for T, that we use S to estimate sigma. Okay, well, we do. We have a sample standard deviation. It's right there. Okay, so we meet that requirement. Do you remember what the second requirement is for T? Yes, it's going to be having an approximately normal histogram, and I can say that in different ways. Roughly bell-shaped, symmetric and centered about the mean, and bell-shaped, approximately normal. Hopefully, as you've been going through the notes, kind of making note of the different ways that I can say that, okay? So we have our histogram up here, and we kind of started with saying, well, that is a very clear left skew. The histogram is not approximately normal, okay? So no, we do not meet the requirements for t, okay, because we are not sampling from an approximately normal population, okay? And again, that's evident from the picture of the histogram that we see up here. Okay, so if we're talking about an average problem, that means we can't use what we learned about proportions in case study 1, okay? And it means we don't meet the requirements for the test statistic that we use in case study 2A. So we're gonna need a new test statistic for case study 2B. And anytime we need a new test statistic, we have to start off with a theorem. All right, so this is the central limit theorem, okay? Notice that this is the formal central limit theorem, and then this is the summary, okay? I'm gonna talk about both of them. Suppose a random sample of size n is collected on a variable. If the population of possible outcomes for this variable has mean mu and standard deviation sigma, then provided n is large, x bar has an approximately normal distribution. Okay, that's one of the big takeaways, okay? We're talking about x bar. When n is large, x bar has approximately normal distribution. The mean of x bar is mu, and the standard deviation of x bar is sigma over square root n. Okay, notice one of the symbols in there a lot is x bar. The central limit theorem is about x bar, okay? This right here, I'm gonna go ahead and get a different color in here. This is gonna be your big takeaway. Provided n is large, x bar is what has an approximately normal distribution, okay? Now that doesn't mean that just the more samples we take, like if I just took more samples up here, eventually that's gonna look normal. This histogram is always going to be left skewed. But the idea with the central limit theorem is, try to picture us all sitting in class right now, and there's, maybe about 30 of us in class, okay? And let's say I collect 90 students' GPAs and I have 1 X bar, okay? You then collect 90 students' GPAs. Now you have 1 X bar too. Let's say the other 29 students in the classroom all go out and collect a sample of size 90 and they all have an X bar. Okay, so 30 students in the class plus me, that means we have 31 sample averages, 31 X bars, okay? What the central limit theorem tells us is that if we were to graph those X bars, okay, X bar is what has an approximately normal distribution. Okay, so let's read the central limit theorem summary. No matter the features of the population being sampled, the sampling distribution of the statistic X bar is approximately normal when the sample size is large, okay? As the sample size increases, this approximation becomes better and better, and the standard deviation among X bar values becomes less and less, okay? Again, talking about X bar here. So going back to no matter the features of the population being sampled, so even though I took a sample of 90 GPAs and the histogram looked left skewed, if I collect a bunch of X bars from the same sample size, the same large sample size, okay, that sampling distribution of your statistic X bar is approximately normal. Okay. Again, X bar is what the central limit theorem is all about. Okay. So, do you remember our standardizing formula? Okay, we've used this in every case study that we've looked at since case study 1B. Okay, this is where we kind of start when we're trying to form our test statistic. Okay, so let's start with our standardizing formula, and then we're going to use the information that we have up here in our first central limit theorem formal. Okay. So what we can do is we can standardize X bar, okay? Central limit theorem is all about X bar. X bar is what we want to standardize. Okay, so when we want to standardize X bar, we plug X bar in for our X variable, all right? Now we need to know, well, what is the mean of X bar and what is the standard deviation of X bar? Okay, and that's given in this central limit theorem formal, okay? This last sentence here. The mean of X bar is mu, and the standard deviation of x bar is sigma over square root n. So I'm going to plug in mu for the mean of x bar, and I'm going to plug in sigma over the square root of n as the standard deviation of x bar, okay? So just to be clear, we use this and this to give us this formula that is based off of our central limit theorem. Okay, so if you look back and you kind of, after you go through these notes, set them next to your case study 2A notes, and we follow a similar pattern, okay? Now that we're here and we have this formula based off our central limit theorem using our standardizing formula, we see one issue that we might have, okay? Sigma, okay? What is the name, the general name for that symbol sigma, okay? Sigma is a parameter, so it comes from the population, and sigma represents the standard deviation, okay? So sigma is the population standard deviation. Populations, those are unknown, so I don't have a value to plug in here for sigma. So what are we gonna do? We're gonna use S to estimate sigma, okay? So when we use S to estimate sigma, I'm just gonna plug in S because S is the sample standard deviation. That's something that will always be given. I'm gonna plug in S to estimate sigma to leave me at this formula here. Okay, I want you to make a note. You need to know this. This is our test statistic for case study 2B. Okay, you should notice that this formula looks very similar to the t-test statistic that we had. This is why it's so important that anytime you write the test statistic formula, you have to write the letter as well, because that's letting me know that you know which case study we're in, okay? And this all goes back to having a large sample. We built this test statistic based on our standardizing formula and the central limit theorem. And what is something the central limit theorem says in the formal and the summary is that when the sample size is large, okay, provided n is large. And we're going to consider n is large as n being anything bigger than 50, okay? And so that's for both case studies, all right? Anytime n is more than 50, okay, that's when we're going to consider it a large sample, and we're going to go with our case study 2B method. Okay, so every test statistic also has a corresponding confidence interval. So here is your confidence interval that corresponds to that test statistic. Okay, again, this should look very similar to the confidence interval for T, except now we're getting our values from the Z table, not the T table. All right, just a little reminder about significance level and confidence intervals. When alpha is 0.01, we choose a 99% confidence interval. When alpha is 0.05, we choose a 95% confidence interval. And if alpha is 0.10, then we choose a 90% confidence interval. Okay, so now we're just gonna go get some case study 2B practice. This is where I'm gonna end this first video, okay? And notice that, I'm talking about this Z. This is gonna be our Z table, okay? So we're gonna be using the other side of your T table now. We're gonna be using the cumulative standard normal, which we did already learn about before we left for spring break. So let's go ahead. We'll start with that next note set and kind of remind you of how to use that table.